Okay.
All right. Oh, Victoria's here, in the Zoom.
Okay, well, we'll go ahead and get started. I'm really pleased to be able to introduce Winter for her presentation today. She's going to be talking about a data set. She did a lot of sophisticated statistics on the data set that were generated by a very large number of staff and students. So I did want to start off giving a really detailed acknowledgement to all of the people that have contributed. This project started in 2008. Of the 24 folks up here who are staff, half of them are students that had graduated from Coastal and then come to work in the lab, usually because they were doing student projects in the lab. So they had a lot of training, and it is a real win-win for the lab and the students. And that they, after a year or two or three, moved on to other graduate programs or jobs out of the area. So I did want to recognize all of their contributions, as well as the data that Winter will be showing that comes from the United States Geological Survey. They've been really good partners with us. We appreciate how much data that they've generated that was also done in collaboration with the same funding partner as supports the water quality work that we're doing. Two of the students that graduated from Coastal did go to work for the local USGS. So in some way, they played a role in generating some of the data that Winter is going to show. I did want to also acknowledge the IT support that we've received from Coastal, because all of the data water quality data that Winter is going to be showing today is publicly accessible from a data portal that Coastal maintains on its website. So you can click here yourself to look at graphs and other types of stats. There is a DHEC, Department of Health and Environmental Control, approved project plan for this project. So in addition to the data being certified by the state, the whole project as a whole has been certified. So it can be used for regulatory purposes. With that, I'm going to give the floor over to Winter. I did also want to take a moment to thank you very much for the work that you've done. We had wanted to do this kind of stuff for years. It really wasn't possible until you have a data set that's this long that you can attempt to do the things that Winter has done, but you also need someone who's very ambitious, competent, and did a lot of problem solving to get it done. So I want to thank you very, very much for this.
Thank you. All right, everybody. Hello, my name is Winter Widdifield, and I've been working at the Environmental Quality Lab for the past 2 years as my internship during my grad program. And at the lab, I conduct various different field work and lab analyses. And another part of my internship has been to create my own individual project with the help of Dr. Susan Liebes, where I will be observing and characterizing trends in the water quality indicators of cultural eutrophication in the Waccamaw and PD rivers. So the Environmental Quality Lab, like Susan said, is a certified environmental lab by the South Carolina Department of Health and Environmental Control. And at the EQL, I have participated in most of the ongoing projects listed here: the Long Bay hypoxia monitoring, beach monitoring, river gauging, and Crabtree Canal microbial source tracking. For each of these projects, I've been responsible for going out in the field and collecting samples, as well as maintaining chain of custody records and completing field data sheets. And then once those samples are brought back to the lab, I will process them and conduct the various lab analyses that we can see here. For every element of my involvement in this project, I've been expected to maintain quality assurance as well as submit my work for quality control. And from this point forward, I'll mainly be talking about my individual project that is done in relation to the river gauging project. So the river gauging project has been conducted for the past 14 years in support of the National Pollution Discharge Elimination System Phase 2 Stormwater Program. And this is a part of the Federal Clean Water Act, which aims to protect, preserve, and improve water bodies from stormwater runoff that is polluted. So all of our 8 sites are indicated with the yellow pins, and this is the Waccamaw River and the PD River. We have 4 sites that are located along the main stem of the Waccamaw, and then 2 are tributaries, 1 along the PD, and then 1 past the confluence of the 2 rivers. And each of these 8 sites, we monitor bi-monthly to determine normal conditions and eventually look at long-term trends. All 8 sites are co-located where USGS sensors are already placed to they are continuous in situ monitors that take a reading every 15 minutes. And these sensors collect limited data, and it varies from site to site what parameters are included. But then we go out and we use a YSI ProDSS to make in situ measurements and then also collect grab samples, bring them back to the lab, and conduct lab analyses on them. So for my individual project, we looked at the parameters total phosphorus, or TP, total nitrogen, or TN, and then also chlorophyll A. So our goal with TP, TN, and chlorophyll A is to evaluate the relationship amongst these nutrients and chlorophyll A, which can also help us to identify seasonal trends and explain abundance levels. So TP and TN are commonly known as limiting nutrients for the growth of algae, which can be represented by chlorophyll A. And whenever the concentrations of these nutrients are exceeding normal values, this can lead to an overgrowth of algae. Whenever there's an overgrowth, it can lead to a bloom, and those blooms can have a lot of detrimental effects, such as creating a layer on the surface, blocking the penetration of sunlight to the bottom, also preventing gas exchange from the atmosphere and the water. And then also when the algae and the consumers of that algae eventually die, the bacteria that come and decompose the detrital organic matter will severely deplete those oxygen levels and lead to anoxic or hypoxic conditions where a lot of animal life cannot survive. So where do these algal blooms come from? Well, the process is called eutrophication, and this occurs naturally in the environment, but also culturally. The cultural eutrophication is caused by runoff from agricultural land or wastewater treatment facilities that include, the runoff includes higher levels of nutrients and chemicals. And so how do we determine if there is cultural or natural eutrophication occurring? Well, it gets a bit difficult because you need to have a benchmark. And for our study areas, there is no benchmark. So the EPA recommended that states make water quality standards based off of the 75th percentiles of data, but we don't have those here, so we're at a disadvantage in answering the question of, is cultural eutrophication occurring? And also, so since the EPA suggested that states did that, that was in 2000, so part of my individual project is to fulfill that request from 23 years ago. Another reason why it's really important to look at cultural eutrophication in our specific study areas is because the Waccamaw River is a black water river, and that means that it has a naturally low level of oxygen. And so it has a low assimilative capacity for any substances that are oxygen demanding, like a detrital algal bloom. So in order to make these water quality standards, we need to know what parameters we need standards for. So the indicators of culture eutrophication come in two categories. The first are stressors. These are the pollutants themselves. And usually for culture eutrophication, we look at total nitrogen and total phosphorus. And then the other category is a response variable that signifies if the pollutant or stressor is having a significant response or a significant impact on the water bodies. So the response variables can be dissolved oxygen, turbidity, or chlorophyll A for this project. We did look a little bit at dissolved oxygen, and we could see evidence of algal activity. So here on the left, we have a graph of Buck Creek, and then on the right hand, of Highway. And these were all taken by the USGS Institute continuous sensors in July of 2022. And we can see every day we're having a low, and a high at Buck Creek. The freshwater water quality standard is 4.0 milligram per liter. And anything below that, fish and animals are starting to get stressed out by the low levels of oxygen. So when we look at the percent saturation, we're also seeing every single day there are reaching a percent saturation of above 100%. And anything above 100% is evidence for the presence of an algal bloom, meaning that there's a lot of photosynthesis occurring. However, when we look at Highway 9, we are seeing a midday high and a low at night, but it's just a muted response. This could be for a variety of reasons. The first is that Buck Creek is a shallow water body where sunlight can easily penetrate to the bottom. And also, because Buck Creek is a tributary and Highway 9 is along the main stem, we are seeing more effects from that Blackwater River low oxygen level. Also, it's important to note that the USGS sensor at Highway 9 is located only 1 foot off the bottom, and that can be up to 25 feet deep. So much deeper water and more of a Blackwater River effect. And so that's why looking at the oxygen is not as clear of an indicator as chlorophyll A, which we'll be using in our project. So the first step to identify these water quality standards is to identify which sites have significantly higher levels of these parameters. So this, a picture like this is going to be occurring in the next few slides. So I just want to go ahead and explain it a little bit. So we start at Buck Creek and move south to Hagley Landing. Buck Creek is right south of North Carolina, and then Hagley Landing is upstream of the Winyah Bay, which I'm sure everyone here is familiar with. We also have Galvin's Ferry, which is our only site located in the PD, and we have Crabtree and Buck Creek, which are our tributaries. Also, really quick, these are your standard box plots where the line in the middle is the median, the boxes are 25 and 75, and then the tails are 10 and 90. So the period of record for chlorophyll A, also just to make sure, this will be experiencing a tidal effect at low flow from Reeves Ferry south to Hagley. So the record is going from 2008 to 2022, and each site has a total of about 340 samples per site. So to find these differences from site to site, we did a non-parametric ANOVA test, and we also generated box plots as a visual indicator of which sites have significantly higher levels of these parameters. So after the ANOVA post hoc tests were generated and the numbers from them are displayed in the middle of the boxes, these showed any the amount of comparisons that were significantly different from this site to the others. So the maximum amount that you can have is 7. For chlorophyll, we're seeing that most of these sites are experiencing vastly different chlorophyll concentrations from one another. We also are seeing that Hagley Landing and Crabtree Canal are having high chlorophyll levels, and Buck Creek is experiencing higher chlorophyll, but to a lesser extent than our other two. The last thing I want to mention on this is that the EPA has recommended water quality thresholds. I'll be talking about that in a couple more slides, but it is 0.4 for chlorophyll A, and we can see that our median values are exceeding that at every site. So then when we look at total phosphorus, the record period did change. It is now from 2012 to 2022. This is because of a method change in 2012, and we did check the significancies of the differences, but just out of an abundance of caution, we decided to just use the 10-year time frame. But when we look at the significant differences, we can see each site that has many significant differences is indicated in red, and we have 4 sites that are experiencing 7 significant differences from the other sites. And then we also are seeing that Hagley Landing and Crabtree are experiencing high TP. Butt Creek has an anomalously large range for TP. And then also Gallivan's Ferry, our PD site, has high TP. And then the threshold was 0.05, and 4 of our sites are experiencing higher levels of TP than the EPA threshold recommends. So then when we look at total nitrogen, we see that the 2 tributary sites are experiencing low levels of TN, and the only site with higher TN than the EPA recommended threshold is Highway 9, and this threshold is 0.9. So we have seen some evidence for eutrophication related to elevated total phosphorus levels. This can be seen at Hagley Landing and Crabtree, and then also a little bit at Butt Creek with the large range. But we expected for all of the sites that have high TP to also experience high chlorophyll. However, that was not the case with Gallivan's Ferry. And that might suggest that there are some nutrients or micronutrients that are present in the Waccamaw River that might not be present in the PD, and maybe that is stimulating growth of algae. Or alternatively, there might be a toxin present in Gallivan's Ferry that's not in the Waccamaw that is limiting the growth of algae. However, we do run a toxicity bioassay in the lab, and the results did not show that there was a toxin present. So the EPA guidance doc from 2000 had certain protocols that they recommended for proposing water quality standards. And the goal of these water quality standards was to make a benchmark to determine normal conditions and then ensure that the water bodies that you're looking at are healthy enough to support the designated use. The designated use of our 2 rivers is animal life. And in this guidance doc, they did make thresholds, which is what I've been referring to in the monthly box plots, or in the site-to-site difference box plots. And so the EPA recommended these water quality standards based on the 75th percentile and reference streams. But it's important to note that none of these reference streams contained data from the Waccamaw River. So it's not necessarily applicable to our sites. And the 75th percentile supports the Clean Water Act way of making the impairment determination. So under the Clean Water Act, if over 25% of your samples in a 5-year period exceed the water quality standards, then it is determined impaired. And if something's determined impaired, then within 13 years, you have to make a plan in order to reduce the pollutant load and return that water body back to healthy conditions. So we set out to make our own water quality standards. These are the proposed water quality standards from the EPA using our ecoregion. And when we look at this, for total phosphorus, we're having 3 of our 8 sites are higher than the EPA recommended threshold by a lot. We have total nitrogen, 6 of our 8 sites are higher, and then chlorophyll, every single one of our sites is much higher than the EPA recommended threshold. Even Gallivan's Ferry, which was our lowest chlorophyll, is almost double what the EPA recommends. And since this is especially for chlorophyll A, this is definitely evidence of eutrophication potentially occurring. And so since they are so much higher, we decided to propose our own water quality standards, and we explored 3 different options. The first was to make kind of a blanket water quality standard for each of our 3 parameters. However, since we already explored the site-to-site differences, you could see there were vast differences amongst all of the sites for most of the parameters. So then we looked at a second option, which was grouping our sites by hydrological features, such as the 2 tributaries and the Waccamaw main stem. But this didn't really encapsulate exactly what we were looking for, and it seemed to have some conflicts with our tributary sites. So we decided to look at a third option, which was to use the individual 75th percentiles and then make a low, medium, and high group of water quality standards. So for TP, we can see the low group fits within the EPA water quality standard, but then the medium and high group are definitely higher. For total nitrogen, we have our 2 tributary sites lower than the EPA recommended, but then all 6 of them much higher. And then for chlorophyll A, you can see all of those much higher than the EPA standard. It's also interesting to note that Florida is the only state in America that has all 3 of these water quality standards already made by the EPA recommended procedure. And so we see that total phosphorus and total nitrogen are higher in Florida, but then this chlorophyll A value is much lower than our 2 sites that are experiencing high levels of chlorophyll. So this is, again, just some evidence for potential eutrophication occurring. The EPA also recommends to potentially use seasonality to define your water quality standards. And this might be appropriate for our 3 parameters that we're using, since they do have seasonal variability. So these monthly box plots were generated to visualize the seasonal effects. And to test for these differences, we performed non-parametric ANOVA, and then again, we generated those post hoc tests that show the comparisons of significant differences, and the ones with the lots are indicated with red, pink. So for chlorophyll A, we do see a pattern of the concentration being higher in the summer months, June, July, August, and then lower in the winter months, November, December, January. We also did see every site have a significant seasonal variance for chlorophyll A. So then we looked at TP, and we see that it's following a very similar pattern. It is higher in the summer months, May, June, July, and then lower in the winter months, December, January, and February. And again, almost every site had a significant seasonal variance for total phosphorus. So then total nitrogen is also experiencing a seasonal variance. It's just not as clear as before. So we see here that it starts being a higher concentration in April, and it goes all the way to September. And then it has a lower concentration in the winter months of December, January, and February. And for all of these monthly box plots, I've been showing you an example at Highway 9, but we did create these ANOVAs for every single site, and they were all showing significant seasonal variance, except for total nitrogen at Hagley Landing. It showed no evidence of seasonal patterns. So then since we identified the seasonal signal and trend at all of these sites, we wanted to see if there was a long-term trend to show if indicators are getting worse over time. So to do that, we used the seasonal man-Kendall test using the citation and computer code. And this is an example of a graphical output of a seasonal man-Kendall test. So here we have the time series of chlorophyll concentration. And then this is at our Crabtree tributary site. So at the start of our data set in 2012, we had 1.5 microgram per liter. At our end of our data set in 2022, we have a 3.4. That red line shows the linear trend equation that is output from the seasonal man candle test. And it's showing that we have had an increase of over twofold of chlorophyll since 2012. And this is a test that is used by the South Carolina Department of Health and Environmental Control on their ambient water quality monitoring data. And it does require 10 years of data, so we were just now able to run it. But to look at the summary of what we found from the seasonal man candle test, we see that Gallivan's Ferry has a moderate or strong increase for every single one of our parameters. For chlorophyll A, we're seeing almost every single site except for one is experiencing some form of increasing trend. For total phosphorus, every single site except for Hagley is increasing or is experiencing an increasing trend. And then for total nitrogen, it's sort of a mixed bag if it's increasing or decreasing. But from the seasonal man candle test, one of the biggest limitations is that it is subject to serial correlation problems from the rigid assumption of seasonal behavior, and then it also doesn't include discharge data. So this is discharge data taken from USGS over the course of our river aging project. So here, since we have this discharge data, it does experience some seasonality, but it's mainly defined by extreme weather events over the course of time. So these are like decadal scale climate change or increase in hurricane frequency or intensity. And because these events dominate the discharge trends, it's difficult to resolve any anthropogenic alterations. So taken from the indicators of hydrological alteration from the Nature Conservancy, we define the floods and droughts up here. So we have 7 floods occurring in the middle of our data set, and then 9 droughts occurring at the beginning and end. And even though there were all these extreme weather events, it ended up that there was no long-term trend in the discharge because they were sort of balancing each other out. So a better approach to evaluating this water quality trend in these rivers is to use the USGS weighted regression on time discharge and seasonality. This approach does not require a rigid assumption of seasonal behavior, and it also includes discharge data. But the program does have cons, which we'll talk about a little bit later. And we were only able to run it on 2 of our sites, which is Highway 9 and Gallivan's Ferry. And these are some of the examples of graphical outputs you'll get from WRTDS. Here we have the flow normalized concentration, and we can see that it looks like there is an increasing trend, but WRTDS also provides a description of likeliness of trend as well as an estimation of the magnitude of trend given by a consensus of 200 bootstrap simulations. So we could see that it looked like it was increasing, and then WRTDS told us it was a highly likely upward trend of about 75% increase of chlorophyll A since 2009. So then we also needed to look at the flow normalized flux. Flux is really important, especially getting back to that Clean Water Act, where if a site is determined impaired, then we have to make a plan within 13 years. And the way to write up that plan is by terms of reducing the load of pollutant. And flux and load are synonymous in that they are equal to the concentration times the discharge. So for example, if there was no trend in concentration, but there was an increase in discharge, that can still increase the load of the pollutant. So for management purposes, it's really important to look at both concentration and flux. And so whenever we look at these graphical outputs, we're seeing that there seems to be an increasing trend, and then the WRTDS tells us that it is a highly likely upward trend of, again, 75% increase in chlorophyll A flux since 2009. And since there was such a high increase in concentration, the higher flux is likely caused by that increase in concentration, since again, we did not see a long-term trend in discharge. So up until this point, we have found some evidence for cultural eutrophication. Those pieces of evidence are that some sites have markedly higher levels of total phosphorus, total nitrogen, and chlorophyll A than others. Also, comparing our 75 percentiles to the 75 percentiles made from the reference streams that the EPA looked at, we're experiencing much higher levels, especially for chlorophyll A and total phosphorus. And then also, some sites are showing increasing trends in total phosphorus, total nitrogen, and chlorophyll A. So what are some possible anthropogenic sources of this? We use the USGS spatially referenced regression on watershed attributes, also known as the Sparrow model. And these are annual aggregated yields that look at the percent contribution of these sources. So for the Petey River, that is identified with green, and the Waccamaw with red. And for the Petey River, the main source of total phosphorus was wastewater. And then again, for total nitrogen is wastewater, also farm and atmospheric deposition. And then looking at the Waccamaw River, we're seeing that the main source is manure for total phosphorus, and then also manure for total nitrogen and atmospheric deposition. And that's likely because of the confined animal feeding operations in North Carolina. So all of these have been evidence for cultural eutrophication, but there is an argument to be made for natural eutrophication, especially when looking at this natural source of total phosphorus there. So that natural source comes from the underlying rocks, which are of marine origin and contain carbonate fluoroapatite, which will increase the levels of total phosphorus in the groundwater. So whenever the groundwater seepage occurs, you'll have higher total phosphorus in your rivers. However, it doesn't really explain why total phosphorus and chlorophyll A are increasing at some of the sites. And that really makes the argument more for cultural eutrophication rather than natural. And some of these anthropogenic impacts could include changes in rain or climate change. So then we thought we should look at the causes of the seasonality of these parameters. And so we saw that TN and TP are highest during the summer months. What else is most likely occurring during summer months? More agriculture. So there is just going to be more fertilizer and manure occurring in the summer, increasing the load. And then also there is more precipitation in this area in the summer, which will lead to more runoff. There's also, when we look at the TN to TP ratio, it's lowest in the summer. And that might say that the total phosphorus, the fertilizer is more enriched in the total phosphorus that you're using, as well as there might be denitrification occurring in the water whenever the oxygens are the lowest in the summer. So I wanted to get back to the WRTDS for a second when looking at what we can do in the future. So like I said, we were only able to do WRTDS for 2 out of our 8 sites. This was for a couple of different reasons. The first one being that there just wasn't discharge data available at all of our sites. You need at least 10 years, and there were only a couple, I think only 4 sites had actually 10 years of some kind of discharge data. Most of the other ones only had something like gauge height. And then another issue is that the way that the regular WRTDS works is that you use the discharge parameter, but it can't have too many negative numbers. And those negative numbers are caused by the reversal flow and tidal effects. So when looking at Reeves Ferry, it had too many negatives to run the WRTDS model. We thought it might be helpful to compare Highway 9's discharge with Reeves Ferry's discharge to see if it was a good proxy. And we got an R-squared value of 0.88. And this means that there's a pretty good correlation with the discharge, and it might make a good proxy. So downstream of Reeves Ferry, where there is a much stronger tidal filter or tidal effect, we did look at tidal filtered discharge. And the issue with Conway in particular is that Conway has the tidal filter set to 24 hours. And so it still contains negative discharges. So one of the ways to solve this might be to try other filter periods, like maybe a 12-hour, 25-minute period of the tides, or oh, and another issue is that this site had big gaps in our discharge data. So it actually, even though it had 10 years, it had like a year gap in it, so it wasn't able to run. So again, when we looked at the Highway 9 compared to the tidal filtered discharge at Conway, it did seem like a good proxy. The R squared is 0.85. And so because we've looked at these two graphs where they do seem to have a pretty good correlation, there might be justification to use Highway 9 for the sites that are downstream of Conway, and just use the gauge height or water level to calculate a discharge value for them and make sure that they're a good proxy, and then potentially use Highway 9. So from this project, we have seen evidence of eutrophication. Now, is that natural or cultural? Well, the indicator correlation or concentrations that are compared with the EPA threshold is definitely making us lean towards cultural eutrophication, since especially for our chlorophyll and total phosphorus, it's having much higher elevated levels of concentration. We also didn't really find clear evidence of the limiting nutrient status between total phosphorus and total nitrogen and chlorophyll. And that's because for the PD River, it had anomalously low chlorophyll, especially whenever looking at the elevated total phosphorus levels. Another evidence for cultural eutrophication is that we were seeing total phosphorus, total nitrogen, and chlorophyll A increasing at some of our sites. And this might lead to some concerns for harmful algal blooms occurring. And this is an algal bloom from Buck Creek, and this is the USGS sensor that we look at. And then also, we have proposed a set of water quality standards. And so in the future, just looking at those and making some seasonally defined water quality standards would definitely be a good future project to work on. And then finally, we've really determined the importance of a long-term data set. Like I said, a lot of these tests that we've done haven't even been able to run until 2022 because they needed full 10 years worth of data. As you can add more and more years, this will just make your trend predictions more accurate. And also, we've learned the importance of having discharge monitoring data at every site. Is very frustrating only being able to work with 2 of their sites for the WRTS model. And the more parameters that you can add to look at these trends, the more accurate trend you'll be able to get. So definitely looking forward to in future years, once the record period gets longer, hopefully they can add some more sites to that WRTS model. And finally, I just want to make some acknowledgements. I know Dr. Liebes made some in the beginning, but I want to thank the environmental lab quality staff since 2008 for working really hard on this river gauging project, going out in the field despite any sort of weather conditions, and also conducting all of those lab analyses. Also, Danielle Bezo, our EQL director and my supervisor, Dr. Susan Liebes, my advisor, Dr. Angela Hinias, and Dr. Aaron Hackett, my committee members, as well as Oregon, Georgetown County, and the City of Conway for funding this project for the past 14 years. That's it. Thank you. Does anybody have any questions? Yes.
That was an excellent presentation.
Thank you.
Why is Haggard so high?
That's a great question. We talked a lot about what might be potentially causing all of these high phosphorus levels and high chlorophyll. We were really hoping to find the evidence that the high total phosphorus was causing high chlorophyll, but we do see that Hagley is located downstream of several wastewater treatment plants. So that could definitely be increasing the total phosphorus. As far as the chlorophyll, it could be phosphorus limited. We would have to do assay to determine that by adding fertilizer to the sample and seeing if the algae would grow. But we definitely haven't been able to prove that TP is the limiting nutrient yet. But I would say for TP, definitely the wastewater treatment plant is contributing.
Nothing else did, so that makes sense.
Yes.
I have a few different questions, but I'll ask some policy questions first.
Okay.
These standards were supposed to be developed 20 years ago.
Mhm.
Obviously, if they were developed 20 years ago, they would be different standards that are developed today.
Yes.
So what does it mean if your standard is developed on an impaired waterway? Is the standard really just showing that it's getting worse or better compared to today? So today's snapshot, whatever it is,
Mhm.
then we're measuring relative to that, or how does that, how do you interpret that situation?
Well, I think, first of all, you can always be updating water quality standards. So one option, like the Clean Water Act has stated that after 5 years, if the water quality is over 25% of the water quality standard, or if over 25% of your samples are over the water quality standard, then that's what's considered impaired. But also, if it's already impaired and you can see that the water quality standard is always exceeding more than 25% of your samples, then you can create new water quality standards, but also it doesn't take away the fact that it's an impaired site, but it will help you in your remediation strategies afterwards. So like, for example, a lot of these strategies are done by looking at flux. And so if you are quantifying and seeing how much flux, that will help you to determine how much flux you want to decrease by to return to your standards. So it's definitely, it does feel like a little bit, you're making water quality standards on an impaired water body. What's the point of doing it? But it does help to help define how bad it is and how much you want to reduce that load by over time. Does that answer your question?
Yeah.
Okay.
I mean, I guess you're saying that it's more about monitoring whether the conditions are improving or declining relative to the time, to the point in time when that standard is developed.
Yeah.
And then if it actually improves, and that's how your remediation is working, and you can readjust the standard when it gets better.
Mhm.
That makes sense. Can you go to the slide real quick where you showed like it was significantly different? I think it was the phosphorus in the winter versus summer.
Yes.
It was just kind of a practical question about all these plots. And then where is the reference? Like this test work by like comparing two different things, right? Like you're always comparing one against the other to see if one is significantly different than the other.
Mm-hmm.
So are you comparing like month to month, or you're comparing like January to July? Is it always compared to July, or where's the control?
So we actually use crossplots to identify these numbers, and we compared January to every single month, February to every single month, and then these numbers indicate the significant differences that it had between all of the different months. So like, for example, April and May, I'm not 100% sure for this data set, but April and May might not have had a significant difference from one another, but it did have a significant difference from July. So that was what we did. We compared everything every month to each other.
So when it has like 5 there, does that mean it's significantly different than 5 other months?
Yes,
Okay. But you, and then I guess you just know that those 5 other months are not in summer.
yes.
Yeah.
Well, we can see on our cross plots which one it's significantly different from.
Right.
It shows us like that the concentration from July is significantly different from the
Yeah, I remember
concentration.
that picture, I mean, that graphic. You were thinking of what's this?
Mm,
So you have to look at-
yes, the numbers are just from that cross plot to show you that there were significant difference in those months. Anybody else have questions? Yes.
Aaron, her comment, is there such thing in the world these days as a unimpacted Blackwater River that you could compare standards with? I burned it in my consciousness for many Susan talks
Mhm.
that the EPA oxygen standards don't work for Blackwater.
That's a great point. I mean, I am not aware of a Blackwater River that is not experiencing water quality problems, but I feel like we mainly just compare it to the rivers in our ecoregion to look at these. And the Waccamaw River just happens to be a Blackwater River in our region. And they didn't have, I'm not 100% sure if the ecoregion had other Blackwater rivers, but it did not contain any from our sites.
Let me just jump in here because the two questions are related. That, yeah, it's a big problem that we don't have good reference streams or locations because humans have impacted everything. But the real point of doing all of this is for that aquatic life, that you want to make sure the water is of a quality that can support the indigenous natural community. So all of these water quality standards are really proxies that are several steps removed from what the true goal is, which is to make sure the environmental quality supports the aquatic life. Well, why are we doing that? Because, you know, as a biologist, you know that trying to come up with that answer is way harder than just cooking up a number that you can then use from sampling to compare good, bad. So that's why the Clean Water Act went with these discrete thresholds. They were the best that anybody could practically come up with. And why it's been over 20 years since anybody, even doing that, it's taken more than 20 years for states to develop water quality standards. Because we don't have a really clear linkage between these numbers and the actual goal of aquatic health. You know how difficult it is to sample for biota in Waccamaw River, you know, and get an idea of the fish community.
For me, that's still easier than.
I don't know, I wouldn't get in that river. Yeah.
Any other?
I have one last question, if you don't mind. So this one could be a little bit about physical process, because I would be remiss not asking about that, right? So what is the role of physical, you know, the water flow, you talk about the flux, you talk about the discharge. But you also mentioned in the very beginning about water depth. You talked about water depth being a factor with the low DO, differing from the shallow water environment. And so I'm also wondering about things that you didn't mention, like things like the runoff, in the localized runoff in a particular area, how that might differ from one site to another, and how much of a factor that might play into these statistics. And then also thinking about things like, you know, there could be a site upstream, an upstream site that's showing maybe an increase in trend in chlorophyll, and then you see a downstream site that has a decreasing trend in not very many of them, but decreasing trend, does that mean that would you prescribe that difference to do with, you know, some of these things like localized runoff, the amount of mixing, the flow in that area? Or do you think that's all to do with load or, you know, so that's, you know, because, or does that do with consumption by the, you know, aquatic organisms? How, you know, how would you, I guess, I know that's not part of your study, but I'm just, you know, how do you think about those things? Or how would you, you know, untangle that? Or would you recommend to untangle that? Or do you think that it matters?
Well, I don't think that it matters, especially whenever you look at like by localized load or discharge, are you meaning like in the particular sites
Well, I'm just
themselves?
saying, like, if you're in a farm area where the amount of runoff for a given rainfall event
Yeah.
is gonna be different than you have like a big parking lot full of like, you know, cars and, you know, that
Yeah.
kind of thing, right? You're gonna have a lot more runoff in those kinds of areas, but you're gonna have less potential, maybe you potentially have less like, you know, organic and non-organic compounds coming in
Mhm.
that runoff. So, yeah.
Yeah, I definitely thought about that, especially whenever I was looking at the potential sources, especially because like Galvin's Ferry, that's located on the PD River. It's our only one in the PD River. So that one is located in a area where there's a lot more septic tanks, a lot more agricultural land. So to me, it definitely makes sense why that area might be a little bit higher in the TP. And then, you know, Hagley is the only site that's downstream of the confluence. And so, you know, it's getting from upstream on both ends, and it, you know, it's a site that's having high chlorophyll and high total phosphorus. And so definitely I think I've looked at it from site to site to see what sources might be different, what is causing higher levels of the parameters in each place. And then it's also, you know, looking at flow from the agricultural or looking at the total load is important, but then, you know, for the Waccamaw River, you have urban land as a high contributor for total phosphorus. You have a lot more impenetrable land from the cities. So I've looked at a lot of the different parameters. It's just that some of the sites have been somewhat anomalies to me, like Galvin's Ferry for having high TP and then not for chlorophyll. So whenever we were looking at that, we did look upstream of the Galvin's Ferry to see if there might be wastewater treatment plants above that or something that might be killing the algae. And we also looked at the chlorophyll ratio to the phaophytin to see if there was like more dead algae there that might be a reason for that. But we didn't really see a significant impact. So it is sort of a mystery to us why it's like that, but we definitely explored a lot of the different ways that.
Yeah, and I think you did a great job with that. I guess what I'm asking is, like, if somebody else were to continue this work, how, like, what would you recommend is the next thing to look into that you didn't really take into account here that you think might be a factor that would be worth checking?
If somebody got my project after me and had way more experience with like a GIS, I would love to see like land use change over time or how certain wastewater treatment plants are running into different river systems. Or if someone does know maybe more of the computer science base, if they can look more into that WRTDS data that we looked at. And you know, having only 2 sites to look at was very difficult to make a accurate assumption of what's happening across our whole study area. So definitely either a GIS direction or a more computer science analysis direction would be what I would like to see. Anyone else? Yes.
Not a question. but
Okay.
Maybe just check the chat just in case.
No questions in the chat. Yes.
Kind of going going off like you say with Galvin's Ferry,
Mhm.
do you think, I know it's like a huge project undertaking, but like if the wastewater treatment plants maybe try and do some sort of source tracking
Mm,
to maybe determine like where the source, I know it's a huge project to undertake, but like,
yeah, I
do
definitely
you think
think
that would
it's.
help maybe to try and determine what's affecting?
I think it's
Okay.
somewhat worth doing. I think that we do know that the wastewater treatment plant is like, well, especially for like Gallons Ferry, it's mainly from septic tanks. So that's just poor maintenance of the tanks. So it's definitely worth doing, but I think we do sort of know somewhat of the sources. I think it'd be definitely interesting if you could do more like looking into remediation strategies for how to decrease those. That's where I would like to go in the future, but it's definitely worth looking at.
If there are no other questions, thank you very much for coming to the presentation.
Thank you.
Winters Committee is just gonna convene in here after everyone's left.
Hi, Victoria. I'm gonna close the Zoom now.
All right, thank you. Great job.
Oh, thank you.